let's start from here. So I can keep it like this. Let's start with this. Yeah, let's do this. We have seen that given x of s of t as the sum from n equal minus infinity to infinity, that's what we get. The correspondent Fourier transform is given by the sum from n equal minus infinity to infinity of xn e to the minus j omega nts. And we have seen that if we define the cyclic frequency nts, this is this is what we call the discrete time Fourier transform of xn, of the discrete signal. Of course, this is the Diractified signal. Diractified signal. And so, given a discrete signal, we can compute the DTFT as the Fourier transform of the Diractified signal. And of course, given the spectrum, we can recover the original signal, the Diractified signal, as the inverse Fourier transform integral minus infinity to infinity of xs of omega e to the j omega t in d omega. Okay? But we are interested in recovering this. Is right? So we need to undo the Diractification. And we already have seen it that there are infinite ways to undo the Diractification, because I can convolve the Diractified signal with an infinite choice of windows, which they need only to satisfy these simple properties. Okay, so one at the where they're centered, and zeros at NTS. Okay, and we have seen that we have two choices of these windows. Okay. So let's pick up. Let's see what is how the Fourier transform of. So let's now basically know what we can define xn as what, as the convolution between xs of t convolved with w of t, but this is computed at t equal nts. But now we can use the duality property of the Fourier transform, and which tells me that this is equal to 1 over 2 pi integral minus infinity to infinity of what? Of the Fourier transform of a convolution is equal to the product of the spectra. So we have xs of omega times the Fourier transform of the window e to the j omega t in d omega, and all of this has to be computed at t equal nts. Okay? So then now we have the correspondent inverse Fourier transform, inverse discrete time Fourier transform of a discrete signal, which is given by this. Okay? So what do we see here? Finally, I think we nail it down. the Fourier transform of a derectified signal is given by this, in which appears, all the information appears through the discrete signal, okay, which is given by this. But then we are only interested in, when we do the inverse Fourier transform, we are able to recover the derectified signal by means of this Fourier integral. But in reality, now we are interested in recovering just the values at NTS. So in order to do that, we need to do a convolution with a special window, and there are infinite choices for these windows. Once we do that, we can rewrite the discrete signal in this form, okay? Where basically what I did is I applied the Fourier integral, the inverse Fourier transform, by using what is the Fourier transform of the convolution? It's going to be the product of the spectra of these two functions, e to the j omega t integrated over the omega. So now we just have to, you see, there are infinite ways to recover the discrete signal from his Fourier transform, discrete time Fourier transform. So let's summarize these results. And so we start with excess of omega is equal to this quantity here. And then we see that we can recover the discrete signal as the convolution between the derectified signal and any window, any window with few properties. So there is not too much restrictions on the choice of this window. And so we can rewrite it as 1 over 2 pi integral minus infinity to infinity excess of omega w of omega e to the j omega computed at NTS in the omega, okay? Because remember, we need to evaluate this integral at t equal NTS. And that's how, if we define omega equal omega time ts equal to omega at the cyclic frequency, we can, as I showed you before, we can rewrite this infinite sum as e to the minus j n omega hat, okay? And I remind you that omega hat we will only restrict it to the principal branch. It's going to be less or equal than pi divided by 2. But this function is a periodic function with period 2 pi, okay? And then this integral, now we can make the substitution omega hat equal omega times ts, and so d omega hat. Actually, before doing that, let's particularize this integral for the two special windows that we chose. The first choice was the box function. W of t was u of t plus ts divided by 2 minus ut minus ts divided by 2. The correspondent Fourier transform is equal was equal to what? The correspondent Fourier transform was equal to ts times sine of omega ts divided by 2 divided omega ts divided by 2, okay? So for this particular choice, we get x of n becomes what, basically? Actually, I'm gonna redo it here. So x of n equal 1 over 2 pi integral minus infinity to infinity xx of omega times ts times sine of omega ts divided by 2 divided omega ts divided by 2 e to the j omega n ts in d omega. And actually, let me, of course, now when we do this integration, we need to consider the entire signal, the entire Fourier transform between minus infinity and infinity. And we know that this signal is, this Fourier transform is periodic with period basically omega s, 2 pi over ts. Okay? And once we do that, we can now make the, you see, we can bring, actually, yes, I can bring this ts here. And so define omega hat equal omega ts, and so d omega hat is d omega times ts. So you can see I can rewrite the integral, this integral as 1 over 2 pi in minus infinity to infinity xs of omega. Now this is going to be a function of omega hat times sine of omega hat divided by 2, because this is basically omega hat. And then we also have here omega hat. It's going to be omega hat divided by 2 e to the j omega hat n. And then these two things together will give me basically d omega hat. Okay? And this is the inverse Fourier transform of the following signal, of this signal here, the inverse Fourier transform, j omega hat n. So omega hat, yes, will equal omega ts. I already did it. So here we found that we have the discrete time Fourier transform, and here we got an inverse discrete Fourier transform, okay, which is given by this form. And this is fine, okay? So it is a messy integral, but you know, we can handle it. And this integral will recover the original signal, the discrete, only the discrete signal at you know, at the sampling times. Of course, you know, this is not the only choice, because you know, in order to do that, you know, we choose the box window. Alternatively, you can define the sinc function in time, is right? So xn is equal to 1 over 2 pi integral minus infinity to infinity of xs of omega w of omega e to the j omega nts in d omega. But now in time we can choose the sinc function. What is the advantage of this having a sinc function in time? That the Fourier transform, it is simply a box, as you know. And you see that now this integral is pretty easy to do, because it's equal xn is equal to 1 over 2 pi integral between what? Between minus omega s divided by 2 and plus omega s divided by 2 of xs of omega times ts. This is now in the frequency domain is a box function. That's why we can do that. Instead, you know, this function is the famous sinc function. Ts 2ts minus ts minus 2ts. Okay, And then here we have e to the j omega n ts in the omega. And now we get an easy integral because now I can do the same substitution. Omega hat equal omega times ts. So you see I can bring these two guys together. This become d omega hat. And when I do these integrals, omega s divided by 2, this is equal to 2 pi over ts. Exactly, divided by 2, 2 and 2, this becomes pi over ts. So when I do the substitution, I'm going to get 1 over 2 pi integral between what? Between the new variable is going to be this minus omega s ts divided by 2 plus omega s ts divided by 2. Then here I have xs, which is going to be a function of omega hat, e to the j omega hat n in the omega hat. But these are easy to compute because this is equal to what? Is equal to pi over ts times ts is equal to pi. And this is equal to minus pi. So we see that this is equal to 1 over 2 pi integral minus pi and pi of xx of omega hat e to the j omega hat n in the omega hat. And we get another expression of the inverse discrete time Fourier transform. Indeed, let's see if we can summarize these two results. So what we did. We saw that the original discrete signal, the Diractified signal, is given by this infinite sum, given by a bunch of deltas. We have seen that the correspondent Fourier transform is written as a sum of is right? And now, if we want to, this is the Diractified signal. We have seen that if we want to recover the discrete signal, there are infinite ways to recover the discrete signal from the Diractified signal by simply convolving the Diractified signal with a spatial window and then evaluated at t equal nts. And this window now has to have some simple properties. Has to be 1 at 0, and then at the sampling times it should be 0. Okay, so and there are infinite infinite choices for this window. Okay, so wt has to be symmetric, then w at 0 has to be 1, and w at nts has to be 0 for any n different than 0. Okay? And once you have these properties, you can rewrite this convolution as the integral between minus infinity and infinity of xs of tau w t minus nts in d tau, for example. Okay, and of course, as I'm going to I show you that there are infinite ways to choose this window. In particular, now we pick up two choices. And what do we show basically? We show that we have excess of t equal infinite sum t minus nts, and then I can recover xn of t as x of t convolved with wt computed at t equal nts, and of course I can rewrite this integral. I can rewrite this expression in terms of the Fourier transform of the derectified signal, which is equal to this j n omega ts. This can be written as 1 over 2 pi integral minus infinity to infinity of x s of omega times ws e to the j w omega omega nts in the omega. So here now I have the discrete Fourier. This is basically the discrete time Fourier transform of xn of t, and here we have the inverse Fourier transform of inverse discrete time Fourier transform. And as you can see now, there are infinite choices for this window, but they will still give you the same signal. Okay, so the correspondence here is still 1-to-1, but there are infinite choices of the window. And in particular, now I show you that we did the two cases. You can choose, it was a box in time, or you can choose a sinc function. So this is basically wb of t sine of pi t over ts divided pi t over ts. So you see that here we have ts minus ts, 2ts minus 2ts, here's 1. And here we have wa is simply the box function, right? So we saw that xn can be written as 1 over 2 pi integral minus infinity to infinity of xx of omega hat sine of omega hat divided by 2 divided omega hat divided by 2 in d omega hat. This is the first integral form of the inverse Fourier transform. And then we can also write it as 1 over 2 pi integral between minus pi and pi of, oh yeah, I forgot, e to the j omega n, xs of omega hat e to the j omega hat n in the omega hat. So this is the other form that we derive. So, and they are equivalent, okay? So they will return me the same value. But it's pretty interesting that this integral is more complicated than this other one. In application, that's what is the inverse discrete time Fourier transform, okay? So let's see if